welcome to the deep dive. Today we're skipping the endless scroll and really focusing in on something elegant. Geometric constructions. Our mission really is to unlock the thinking behind drawing circles and tangents related to other shapes. We're using a set of geometry instructions as our base.
Yeah, we're looking at things like tangents to circles, those lines that just brush the edge.
Right.
And also circles drawn around triangles or inside them, and hexagons too, regular hexagons specifically.
And it's not just about how to draw them. We want to get into the why, the core logic, those aha moments that connect everything. It's about seeing the ideas behind the drawings.
Precisely. We're aiming to give you that intuition, so you grasp the essence, the underlying principles, without necessarily needing a compass in your hand right now. What makes these constructions work? What are the neat little insights?
Okay, great. So let's unpack tangents first. A tangent, it kisses the circle at one single point, right?
Just one point. A fleeting touch.
So, first case, drawing a tangent where the point is already on the circle's edge. The instructions say, join the center to that point that gives you the radius.
Yep, the radius line.
And then right at that point on the circle, draw a line that's perpendicular to the radius. So a 90-degree angle seems pretty straightforward.
It does seem simple on the surface. But this right here, this is our first big insight. That 90-degree angle, it isn't just like a step in the method.
Okay.
It's fundamental. The radius and the tangent always meet at 90 degrees at the point of contact. Always perpendicular. That's the defining property.
Ah, okay. So that perpendicularity is the tangent, in a way. It's not just how you draw it. It's what it is.
Exactly. That's the aha moment. It connects the radius and the tangent directly. A core geometric truth.
Right, okay. That 90-degree thing is key. Got it.
Yeah.
Now, what if our point isn't on the circle? What if it's just, hanging out somewhere outside the circle? How do we draw tangents from there? That feels a bit more involved.
It has a few more steps, yeah. But the logic behind it is still, well, really quite elegant when you see it.
Okay, walk us through it.
So, first step, you connect that external point to the center of the circle. Draw that line segment.
Okay, point to center.
Now, here's the clever bit. You take that line segment you just drew, and you use it as the diameter for a completely new circle.
A new circle based on that line. Huh.
Yep. And this new circle you draw, it's going to intersect your original circle in exactly 2 places.
Ah, okay. I think I see where this might be going.
So you find those 2 intersection points, then you just draw straight lines from your original external point to each of those 2 intersection points. And bam, those are your tangents.
Wow. Using a whole second circle just as a tool. What's the magic there? Why does that specific construction work?
Okay, now this is where it connects back beautifully. Remember that geometry rule about angles in a semicircle?
Yeah, they're always 90 degrees, right?
Exactly, always a right angle. So when we built that second circle using the line from the external point P to the center O as the diameter, the points where it crosses the original circle, let's call 1A, are such that the angle PAO is inscribed in that new semicircle.
So angle PAO must be 90 degrees.
Yeah.
Because it's an angle in the semicircle we just drew.
Precisely. You're essentially forcing that 90-degree angle between the line from the external point, PA, and the radius of the original circle, OA. And since we already established that a 90-degree angle with the radius is the defining feature of a tangent, well, PA must be a tangent.
That is genuinely clever.
Yeah.
You're using one geometric property, angles, in a semicircle to guarantee another the tangent radius perpendicularity.
Isn't that neat? It just falls into place.
Absolutely. And the notes mention something else. Properties of these tangents from an outside point.
Oh, yes. 2 important things. First, the 2 tangents you can draw from that single external point. They're always equal in length.
So PA equals PB if B is the other tangent point?
Yeah, exactly. Perfect symmetry there. The distance from P to A is the same as the distance from P to B. And second, there's a nice link to algebra here. The Pythagorean theorem pops up.
Oh, of course. Right angles often mean Pythagoras is nearby.
Yep. Using our points P, exterior, A, tangency, and O, center, the triangle PAO is a right-angled triangle because the tangent PA is perpendicular to the radius OA.
Right, at point A.
So you get that classic relationship, PA squared plus OA squared equals OP squared. Geometry and algebra shaking hands.
Okay, tangents feel much clearer now. That construction with the second circle is really the key insight for the external point.
It really is.
Let's switch gears then. Let's talk about circles interacting with whole shapes. Triangles first. The classic three-sided figure. We can draw a circle around it, hitting all the corners.
The circumscribed circle or circumcircle?
And we can draw one inside it, just touching all the sides.
The inscribed circle or incircle?
Let's start with the outside one, the circumscribed circle. How do we find its center and radius?
Okay, for the circumscribed circle, the key players are the perpendicular bisectors of the triangle sides.
Perpendicular bisectors.
Yeah.
So that's a line cutting a side exactly in half and at a 90-degree angle.
Correct. Now, here's the thing. If you draw the perpendicular bisector for any two sides of the triangle, they will always intersect at one specific point.
Only one point, okay.
Yes. And this intersection point, we call it the circumcenter, has a very special property. It is exactly the same distance from all three vertices, all three corners of the triangle.
So if the point is O and the vertices are A, B, C, then OA equals OB equals OC.
Precisely. It's equidistant from the vertices, and that distance, OA or OB or OC, that's the radius of your circumscribed circle. Put your compass point on the circumcenter, set the width to any vertex, and draw your circle. It'll pass through all three perfectly.
So finding that equidistant point is the whole game. And you only need two perpendicular bisectors to nail it down.
That's all it takes. And actually, another neat property is that if you did draw the third perpendicular bisector, it would pass through that very same point. They all meet there.
They're concurrent.
Exactly, concurrent. It's an inherent property of triangles.
Cool. Okay, that covers the circle around the triangle. What about the one inside, the inscribed circle, the incircle?
Right, for the incircle, we switch focus. We don't look at the sides anymore. We look at the angles of the triangle.
Okay, angles now.
We need the angle bisectors, so lines that cut the angles exactly in half. Again, pick any two angles of the triangle, draw their bisectors.
Yeah, let me guess. They also intersect at a single point.
You got it. They intersect at a single point inside the triangle. We call this one the incenter.
Incenter, makes sense.
Oh, no.
And its special property. Last time it was equidistant from the vertices.
This time, the incenter is equidistant from all three sides of the triangle.
From the sides themselves, how does that work?
It means the shortest distance from the incenter to each side, which is always the perpendicular distance, is the same for all three sides.
Okay. So if you drop a perpendicular line from the incenter down to touch any side.
That perpendicular line segment, that's your radius. The radius of the inscribed circle, the in radius.
And once you have the incenter and that radius, you can draw the circle and it'll just touch each side.
Perfectly. And just like before, if you drew the third angle bisector, it would also pass through the incenter. The angle bisectors are also concurrent.
So circumcenter from perpendicular bisectors of sides, equidistant from vertices, incenter from angle bisectors, equidistant from sides.
Got it.
That's the core distinction.
And our notes mentioned that these methods work for any triangle, right? Doesn't matter if it's equilateral or, really skewed.
That's absolutely right. These properties, the concurrency of perpendicular bisectors and angle bisectors, the equidistance properties of their intersection points, they hold true for all triangles. Scalene, isosceles, equilateral, acute, obtuse, doesn't matter.
That universality is pretty powerful. Okay, last stop on our geometry tour today. The regular hexagon. 6 sides, nice and symmetrical.
Yep, the regularity is key here. How do we handle circumscribed and inscribed circles for these? So let's do circumscribed first, the circle going around it.
Okay, so because regular hexagons are so symmetric, we actually have a couple of nice ways to do this. One way is just like the triangle. Find the perpendicular bisectors of any two adjacent sides.
Like side AB and side BC.
Exactly. Where those bisectors cross, that's your center. And the distance from that center to any vertex, any corner of the hexagon, is your radius.
Okay, consistent with the triangle method.
Yeah.
That makes sense. But the notes hinted at maybe an easier way, a shortcut.
Yes, there is, thanks to that beautiful symmetry. You can also find the center simply by drawing any two of the main diagonals.
Main diagonals?
Yeah.
You mean the ones that go straight across, connecting opposite corners?
Yeah.
Passing through the middle?
Those are the ones, draw 2 of them where they cross. That's the center. Dead simple.
Nice.
But here's the really cool part. The surprising insight for regular hexagons. The radius of the circumscribed circle, get this, is exactly equal to the length of the hexagon side.
Wait, really? The distance from the center to a vertex is the same length as one of the sides?
Exactly the same. So if you know the side length, you instantly know the radius of the circle that goes around it. No bisectors needed if you know that fact.
Wow. That feels like a cheat code. Why does that happen?
It comes down to how a regular hexagon is built. You can actually divide it perfectly into 6 identical equilateral triangles with all their points meeting in the center.
Equilateral triangles. all sides equal.
Right. And in that setup, the sides of the hexagon form one side of each equilateral triangle, and the lines from the center to the vertices form the other two sides of each triangle. Since it's equilateral, all those lengths must be the same. The radius equals the side length.
That makes perfect sense when you picture those 6 triangles. Okay, brilliant shortcut. Now, what about the inscribed circle, the one inside the hexagon?
For the inscribed circle in a regular hexagon, we go back to the angle bisector method, just like with the triangle.
So bisect 2 adjacent angles, find the intersection point.
Yep. Bisect 2 of the interior angles. Where the bisectors meet, that's your incenter. Same point as the circumcenter, actually, for a regular hexagon.
Oh, right, because it's so symmetrical. Center's the center for everything.
Pretty much. And then the radius of this inscribed circle, the radius, is the perpendicular distance from that center point down to the middle of any side.
Okay, so angle bisectors give the center, perpendicular distance to a side gives the radius. Similar logic to the triangle again.
Very similar logic. But there's a crucial caveat here, especially with hexagons.
Which is?
These nice straightforward constructions we've just discussed for circumscribed and inscribed circles, they generally only work properly for regular hexagons, the ones with all equal sides and all equal angles.
Ah, so if you have a wonky, irregular hexagon, you can't necessarily just bisect things and expect it all to line up perfectly.
Exactly. That beautiful symmetry, the concurrency, the simple center finding, the side radius relationship for the circumcircle, those rely heavily on the hexagon being regular. If it's irregular, finding a circle that hits all vertices or all sides, well, it might not even be possible, or it's much, much more complicated.
So that regularity is doing a lot of the heavy lifting in making these constructions work so elegantly for hexagons.
It really is. It highlights how important symmetry and regularity can be in geometry.
Okay, so wrapping this up, this deep dive has really shone a light on some core ideas, hasn't it? We've seen perpendicularity being absolutely key for tangents and for bisectors.
That 90-degree relationship is everywhere.
And then there's equidistance, the idea of being the same distance away from points, like the circumcenter from vertices or the incenter from sides. That's what defines these centers.
Absolutely critical.
And we saw concurrency showing up lines that just know to meet at a single point, like the bisectors and triangles or the diagonals and regular hexagons. And of course, that amazing hexagon fact radius equals side lengths for the circumscribed circle. Can't forget that one.
Definitely a memorable one. And it all reinforces the idea that these aren't just, arbitrary drawing steps. They flow directly from the fundamental properties of these shapes. There's a deep logic and, frankly, beauty to how it all fits together.
It really shifts the perspective from just following instructions to understanding why those instructions work.
Yeah.
It feels much more connected.
That's the goal, seeing the underlying elegance.
Okay, so for a final thought to leave everyone with, having explored these constructions, these principles of perpendicularity, equidistance, concurrency, symmetry, maybe think about this. How might these fundamental geometric ideas pop up elsewhere? Not just in more complex shapes, but maybe beyond geometry entirely.
That's interesting.
Could concepts like finding a point equidistant from others, or the importance of right angles or the consequences of symmetry, could they have echoes in, say, design or engineering, or even how patterns form in nature? Where else does this kind of geometric logic appear? Something to mull over.